Hello, welcome to this presentation about single molecule manipulation. My name is Christian Wagner and I'm from the Jülich Research Center in Germany. So I think it's a general observation that the building blocks of life are very complicated, whereas the building blocks of technology are very simple and streamlined to their bare functionality. Now, of course, this is because those nuts and bolts are actually assembled by human hands based on external blueprints, whereas the blueprints of life have to be stored inside the building blocks, which makes them very complex. We are investigating organic molecules on surfaces, which are rather small, streamlined building blocks, if you want, and we manipulate them with a scanning probe microscope that works under ultra-high vacuum at cryogenic temperature and is specifically designed to measure force and conductance at the same time. Now, in this field, we see the same effect. If we just put molecules on the surface and let them do their thing, they will assemble into these beautiful but rather simple patterns. And it has to be like that because you cannot store the blueprint of a complex structure inside a simple molecule like that. So if we want something complex, we have to assemble it proactively, and we can do anything from an IBM logo to a kilobyte of memory. However, these structures are usually built from atoms because it's easy to work with atoms. Now, molecules are more complicated but also more promising. Therefore, what I would like to talk about today, you could call robotic nanofabrication with organic molecules. And the way we do that is shown here. So we approach the tip to a reactive atom inside the molecule, then a chemical bond forms, which is stable enough that you can move the molecule around on the surface and even detach it completely. And with this approach, we actually have access to a large configuration space. We have the possibility of continuous manipulation where any small tip displacement is answered by a small molecule displacement. And of course, we have access to the third dimension away from the surface. And with these properties, I think this approach is very fitting into this topic of molecular machines for two reasons. First of all, it allows us to build molecular devices, which then again can be helpful in designing future molecular machines. And second, we can use this general approach to explore control paradigms at the nanoscale. So first, let's talk about the molecular devices. I guess we all agree that molecular behavior is largely driven by atomic scale electric fields, which are practically everywhere. So for example, this PDCDA molecule that I keep showing has a quadrupole because those oxygen atoms are actually negatively charged. And if we put this molecule on the tip in the way that I showed it before, it will stay there actually in a vertical configuration where it actually becomes a quantum dot, and you can gate that by applying a voltage to the surface. And then this configuration of tip plus quantum dot becomes a sensor for electrostatic potentials on the surface in a method that we call scanning quantum dot microscopy. And given that we have another PDCDA molecule now on the surface, we can really create these beautiful images of the electrostatic potential of this molecule. And as I said, so this is relevant. For example, this quadrupole of PDCDA determines how the molecules order in a molecular island. But we can go further. Here you see an STM image of what you could call a nanoscale construction site where you have many different building blocks. And here is a completely different layer of information. So this is the electrostatic potential. And you can see, for example, that this line or this edge here, which appears very straight, in fact has a very strong electrostatic corrugation, which you could imagine could trap other atoms or molecules. So I think this technique is definitely going to reveal something which would help us to design molecular machines in the future. Now, the second aspect I wanted to mention is nanoscale control. And here I would like to point out especially the role that machine learning has and will have in the future. Now, you could think about it in the following way. The SPM basically has inputs, which is tip position, voltage, etc., and outputs, force gradient, conductance, etc. Then we have an agent which makes decisions that could be either us or it could be an AI. And of course, we have a goal, a target state that we want to achieve. Now, if we introduce a feedback here, then we can really explore control paradigms. And one that we looked into is that of autonomous manipulation with reinforcement learning. And the task we set for the reinforcement learning agent was to remove a single molecule from a layer. Now, what we are in fact playing is this claw game here, and I guess you know it's quite hard, and it's hard at the nanoscale as well, because those PCDA molecules are connected in the layer by a network of hydrogen bonds here. And the agent still has to find a way to remove these molecules. And after about 10 to 20 trials, usually in the experiment, the agent finds that it has to remove the molecule in this kind of peeling motion where it breaks the bonds sequentially. And with this, the agent has, without any prior information, solved a nanomanipulation problem or achieved a nanomanipulation goal on par actually with the performance of a human. The second aspect that I would like to quickly highlight is that of configuration monitoring. So in general, with these experiments, we have the problem, we don't see this configuration. All we see is the output of the SPM, which is nothing else than a line on the oscilloscope, force, current, etc. This is sufficient for the reinforcement learning task that I just showed, but for more complex goals, we would like to have, of course, the configuration of the molecule, atomic configuration, and we want that in real time during the experiment. And that's, of course, very hard. So the way we approached it is shown here. We train a machine learning model based on, or train it with highly accurate DFT data, and then use this model to fill a database with all possible configurations of the molecule. Now, the access to this database is fast enough that we can use it in a real-time loop where we use a VR interface to control the SPM, position the tip, and then a search through this database gives us actually the most likely configuration estimate based on the experimental data we have measured so far. And without further ado, let's have a look how this actually looks like in the experiment. So this is Joshua controlling the SPM with his hands. And here's what he sees in his 3D goggles actually. And so he can manipulate now the molecule in a way as if it was right in front of him. However, I would like to point out that this approach is actually very recent, and we are still working on assessing how reliable it really works. And with this, I'm at the end. I would like to give you a few short conclusions. So I think I showed you that precise three-dimensional control over a single molecule is possible using an SPM. And this approach, while it's of course not capable of making millions of copies of anything, it could really enable something that I would call rapid prototyping, where the functionality of different molecular machines or devices is basically tuned and explored. And the last point is, I think that machine learning will be very important in the future, and I think already now we benefit from it extremely in this field of molecular manipulation. And with this, I would like to acknowledge all my co-workers and collaborators who contributed to this work over the years. And since you cannot ask questions now, please feel free to write me an email if you have any. Thank you very much.